thanks everyone for joining us today for this webinar for Clickable Engineering Mathematics with Maple. What I'm going to be doing over the next about half hour, 45 minutes or so is just kind of going through a few classic examples for undergrad engineering courses and showing you how you can use different features and functionality within Maple to be able to solve some of these classic problems. So what I have laid out here, just three examples. One, working with transfer functions, so doing transfer function manipulations, solving curvilinear motion of a particle, so projectile motion, and then looking at some static examples dealing with truss analysis. So to start things off, actually, I'm just going to go over here to our curvilinear motion of a particle. So for this example, we're going to be looking at a projectile that's fired with an initial velocity of 240 meters per second at a target B located 600 meters above the gun A and at a horizontal distance of 3,600 meters. Neglecting air resistance, determine the value of the firing angle alpha. So this is, again, is a classic first year engineering type problem. So the first thing that we could do here is we can actually create a quick visualization of this within Maple. So what I'm going to be doing is creating a couple of plots here. So I'm going to create a horizontal line and a vertical line, and then basically generate a plot here that will show me basically what I'm trying to achieve with calculating alpha. So I need to find basically a value of alpha that will allow the projectile to hit at this point here where these two lines intersect. So using Maple now, we can actually solve for this problem. So the first part that we'll do here is we'll look at our horizontal motion. So when looking at our horizontal motion, our equations for that are v of x. And as you can see, I have the subscripts located in there, and I'm getting a visual cue from Maple. It's highlighted in pink, showing me that that's that this is a literal subscript on that, not an indexing subscript. So now I can basically put in my equation v sub x is equal to v times cos of alpha. And I'm just going to put a colon at the end because for those of you not familiar with Maple, I'll do this first, is you'll see that if I just press enter, it will echo out my, my input there. But if I come back over here and put a colon at the end of it, it will suppress my output. So just to keep things a little neat and tidy, I'm going to suppress the output on a few of these as I go along. So I'll just give myself a little more space. All right, so now I want my displacement part here, so I'm going to call that S sub x, and I'm going to say that that's V sub x times t plus 1/2 A sub x times t squared. All right, so there are my two horizontal motion equations. Now when looking at the vertical motion, very similar. I'm going to have, instead of v sub x, I'm going to have my v sub y. And what I'm doing here is actually, the reason I'm doing this is because I want to have these equations stored with these names. So later on when I start to manipulate these equations, I'll actually be able to just make reference back to them. So actually if I open up over here in the top left, you'll see that I get a little list of the variable names that I've been using. So I can click on these at any time, and it will actually show me what's being used for what's being stored in that particular variable name. So this is a handy little way to be able to keep track of variable and parameter names that I'm using. All right, so now I'm just going to say S sub y similarly is equal to V sub y times t plus 1/2. This time it'll be A sub y times, times t squared. So now you'll see actually if I don't suppress this output and if I actually have it display, you'll see that it makes the substitution of v sub y in here for me because I have v sub y stored as v times sine of alpha. All right, so I have my initial setup ready to go with this question. Now all I have to do is define some parameters here. So right now I'm going to say, and I just have to re-enter a couple of these in because this is an older worksheet, so I just need to update a couple parts in here. So now I'm saying a sub x is equal to 0, so my acceleration in the x is 0, and my acceleration in the y due to gravity is 9.81, and I'm going to say that my velocity is 240. Okay, so now I have most of my initial parameters set here. So now I need to actually do my calculations. So for my calculations, I just want to show here again, I could say s sub x, and you'll see that that's equal to 240 cos alpha times t. So again, it's taken any of these parameters that I've added in, substituted everything back into those initial equations. So I can also show s sub y, and I get my equation for that as well. So you can see I have two equations and two unknowns that I have to solve for here. I have to solve for my alpha and for my t. So what I'm going to do is I know that my s sub x, based on my problem statement here, so my x position is 3,600 meters. So what I could do is I could just say s sub x, and I can make that equal to 3,600. So that's now giving me the equation, but it's just basically showing me, okay, it's 240 cos alpha and then times t is equal to 3,600. What I actually want to do, though, is I want this to isolate and solve for t. So what I could do, there's a couple of different ways I could do that. One is I could right-click on this, and I could tell Maple to solve this, and I want to obtain a solution for t, and that gives me 15 over cos theta. Or just as easily, I could have typed in the Maple command, which is solve, which is s sub x, and I want that equal to 3,600, and solve it for t. And you'll see it gives me the exact same thing both ways. So similarly, I could actually take this, and I'm just going to cheat up here, and I'm going to rewrite this line. Instead of using that to solve for the s sub x, I'm going to say s sub y, and this is going to be equal to, it had a height of 600, so this is now going to give me my expression for solving s sub y. So as you can see, this is a much more lengthier expression. And what you could do now in Maple is to get a better understanding of what actually is happening here, is I can generate a plot to show me what's actually being, or what these solutions would actually be. Because from a visual standpoint, we're looking for the point where the two lines will end up intersecting or crossing. So I'm going to type in our Maple command to generate a plot. And for the plot, I'm going to say I need two plots created. I want to plot this solution here and this solution here. So you'll see that these have label references 5.4 and 5.5. So within Maple, I could press Control L, and I could say, okay, I want it to give me 5.4. And then again, I'm going to press Control L, and this time I'm going to say 5.5. So I've now created in my plot, I want these two sets, these two plots within my set here, 5.4 and 5.5, to be created. And then the parameter I want it to, or the variable here that I'm using is alpha, and I want that to go from 0 to, let's say, 2 pi. And when I generate this, you'll see that it creates a plot for me here, and I could see various solutions. So because we have our roots in it with our solution and our exponents here, so we know that we're going to get more than one solution, and we're going to get things that are going to be pretty much in the real and imaginary domain. So you can see the solution set that we have here. We have 2 points of intersection here on the top of the plot, and 2 points of intersection here at the bottom of the plot in the negative region. Well, obviously these are ones that we want to ignore, but what we really want to look at is more so up here in the top part of the plot. So I can actually create a window to zoom in around it. And what I could do is I could change my pointer here. And what this will actually do is it's going to give me now what the solutions are for this. So I can go from a visual standpoint, and I could see that my firing angle should be approximately 0.522 radians. And then up here, it should be approximately 1.21. So from a visual standpoint, this is a great way to be able to see our solution, but obviously for engineering standpoints, you want something a little more accurate. You want to actually get the full numeric solution for this. But just keeping in mind, this does give us the answers that we're looking for, but to get the exact answer, I'm going to actually first say that I want to use the real domain because I only want real solutions. And I'm going to tell Maple now to solve. And for this, I'm going to tell it just as I had before. I want equation 5.4. And I want to solve when 5.4 is equal to 5.5. And now with 5.5, you'll see that there actually are two solutions here for it. So I'm just going to tell, just for we only want the part here on the left, so I'm going to choose the first part here. So I'm going to take the first solution that it provided, and I'm going to tell it to solve for alpha. Oh, too many brackets there. And then I'm just going to say end use. And we'll see here that I've got my... All right, something is not... Let's see. Real domain in solve. All right, for some reason it's decided to not solve for my alpha here. Okay, that's odd because I just did this calculation earlier today to verify everything worked, and for some reason it's not showing me the real domain in solve 5.4 is equal to 5.5 of 1 alpha. Let me see if I just, because if I take away this part here, it's probably going to give me solve. All right, just bear with me for a second here, just doing some quick troubleshooting just to see, might not have something parsed correctly in here. 5.4 is 5.5 alpha. All right, so yeah, so there's probably something that when I entered it in, I may have had a space where I shouldn't have had one, because that should have, I want my real domain in. There we go. That's so. I just must have had a space somewhere in there that it wasn't parsing correctly. So these are the solutions that I should get for it. So you'll see 1.21 and 0.52, which, if you recall, when we come up here, our initial guess at what these were, 0.52 and 1.21. So now we're getting the exact answers for this. And what I can actually do with this is I can assign these to a name. So I could say alpha 1. And I'm going to say that alpha 1 is equal to my label 5.6, which is my solution. And I just want it to take the first value. So that's now assigned to alpha 1. And similarly, I'm going to say alpha 2 is equal to 5.6. And it's going to take the second solution. So this is giving me everything in radians, but if I really wanted to, I could take it and I can do an evaluation of it and I can convert it. So I'll just take the first one here and I'll say, okay, take my convert, oops, I didn't need that on there. Convert alpha 1, and I want to convert that into degrees. So you'll see now that it's done the conversion for me, and it's converted it from radians into degrees. And similarly, I could do the same thing with the with my second solution set here as well with alpha 2. So now what I'm actually going to do, though, is I'm going to generate a full visual so that we can see what's actually happening here. So I'm going to generate my plot, and I want to actually substitute in my values here. So I'm going to say substituting with alpha equal to alpha 1, and I want it to plot my s of x. And similarly, I want the alpha to be equal to alpha 1 in my s sub y. Oop, my cursor jumped away from me there. And I'm going to say t is equal to 0 to 50. And I'm going to assign a color to it just so that we can differentiate it. Oh, I'm missing a square bracket over here. So let me just... You know what? I'm going to take out the color command on there. I probably have it. I don't have my color library for this particular color loaded in, so I'm just going to erase that part. All right, so I have my first piece here, and for the sake of time, I'm just going to copy and paste and then just change the names here. So now I'm going to, instead of using alpha 1, I'm going to use alpha 2. And for this one, I'm going to go from 0 to 30. And now I'm going to generate a plot. So using our display command, and we're going to say to display solution 1, solution 2, and then from the beginning, the horizontal and vertical plots that I created. And I'm going to define a particular viewing area for it. And we'll see, oh, all right, it seems to have, all right, so for some reason it's scaling awkwardly the full plot here, but essentially what this should actually look like if I just load up a full version of this here. So at the end, this is essentially what the display will look like. So you can see that we get the horizontal and the vertical, and then it's showing you the two possible solutions and the fact that they do intersect at the particular point. All right, so that just works our way through doing some curvilinear problems with Maple. Now we're going to take a look at a truss example here. So we'll do some statics. And with this, we'll take a look at solving for a particular point here. So we're going to solve using the method of joints. So we'll look at our equilibrium here. So the equilibrium of the entire truss, some of the forces in the x and y and the moments are all equal to 0. And equilibrium at each isolated joint, which is f of x and f of y, are both equal to 0 at that given point. So what I can do down here is I have my sum of the forces in the x, y, and z, or sorry, x, y, and then the sum of the moments. So what I can do down here now is take each of these, and I can say everything in the y direction, and I'm going to say this is 2,000 based on the information that we're given, and I'm going to add units onto this. So I'm going to say 2,000 newtons times 24 meters. Oh, actually, no, this isn't my forces in the Y. This is my moments here, but I'm just going to, actually, I'll just put them all down here. So I'll say 2,000, apply my units to that, 2,000 newtons times 24 meters, plus 1,000 newtons times 12 meters, and then minus 6 meters times, and then for this, I just want to come down here and make sure that I'm going to be using the same naming conventions that we have here. So I'm going to just copy this in. So I have 6 meters times RE, and this is all equal to 0. So again, this is just basically taking the forces that I have and then moving it and summing it about a particular point. So here I'm summing it all about the point C. So now I need to take my RCX, and I'm going to have that equal to 0. And then I'm going to now have minus 2,000 newtons minus 1,000 newtons plus RE plus RCY. So some of the forces in the X, some of the forces in the Y, and then some of the moments. So this is just basically taking all of our information off of this example here. And now we can work our way through and we can take a look at everything at each particular joint. So because I have everything entered in, I can get my equations here that I've already pre-populated. So at joint A, I have my some of the forces in the X and some of the forces in the Y. Same thing at B, I can get my some of the forces in the X and Y. Some of the forces at joint C, D, and E. And now I'm going to actually solve for the unknowns. So when solving for the unknowns, it's basically going to take all of these equations that I have entered in, and again, you can see all of these label references for them. And the last part that I need to do here is actually I just need to add in those first 3 equations. So the first 3 here were 2.1, 2.2, and 2.3. So if I put in 2.1, 2.2, and 2.3. So this is now going to come up with a list of equations that I can solve. And I'm also going to make a substitution here, and I'm going to say that sine theta is equal to 8 over 10, and cos theta is equal to 6 over 10, because again, that's based on the angles that were given here. So we're basically using, well, not the angles, but based on the triangles that we're using here, we can make that use for these types of triangles within the truss. And then down here at the end, we can actually solve for the equations, and I can now get a full list of the solutions with the units for this particular truss. So given the initial conditions that were provided and the dimensions and the forces that were given, I can now take a look and I can calculate the forces and sum them all up within just a couple of lines here with the equations. So the benefit with this now is that now that we have everything solved for this particular case, you could just as easily work your way up here and change around any of these parameter values that are being used, so the forces or any of the reactions or what have you. And then you can just easily substitute the numbers in up here in the initial conditions and then be able to work your way down to the bottom, and then you could solve it for any particular case. So that's essentially what we have here in the second example. So this is now solving the exact same equation, except we're going to just assume that everything is a parameter. So you can see it's just populating everything very similar to what I had in the first example. But instead of putting in numerical values, it's just keeping everything as a parameter. And now when I get down here to the bottom, it can solve the entire truss all parametrically. So now with this, at this point, you can take any of the values that you have here and then just quickly and easily say, okay, solve it for a particular at a particular value. And then it'll make the substitution for this, and then it'll do all the calculations for you numerically, and then you'll be able to solve it for any particular case. All right, so now we'll just jump back to the title screen here, and we'll go through our last example dealing with transfer function manipulation and basically doing transfer functions and calculations within Maple. And what I'm going to start off with in this example is just basically taking a couple of rational functions here and assigning them to my g of s and h of s, and then just basically showing you that you can just quickly manipulate it into an equation of g of s over 1 plus g of s times h of s. But then the next part, I'll show you how you can use some of our interactive components over here on the side, and then be able to make it a little more interactive so that you can explore what some of these values actually represent. So instead of keeping everything as, let's say, as a 1, a 2, and a 3, I can change around some of those values and then come up with a new equation and then make it a little more interactive. So the first thing I'm going to do is assign to the name g. I'm going to say it's a function of s. And I'm just going to, for the sake of time, just copy and paste this in. So what I've done here, this s with the arrow, this is basically what you would normally think would be g of s. But now if I type in g of s, you'll see it just gives me the same equation back. But if I said g of 5, it substitutes in the value 5 for me. So this makes it into this is our function notation within Maple. It is a little bit weird compared to most other software, but this is the way that we need to do it, because the way that Maple works from a symbolic standpoint, everything is basically kind of treated like a function, so we had to change things around a little bit to allow for that type of input. So again, here I'm going to say h is going to be a function of s, and I can now enter that in. So I now have my values saved as g and h. So what I could do is I could just simply say g of s over 1 plus g of s times h of s. And you'll see that it now gives me the equations for it, but I could take that and I can simplify it. So again, I'm going to use the label reference there of 3. And you'll see that it gives me a simplified set of equations. Now with this, I can load in one of our packages, which is called our dynamic systems package in Maple. And what this allows me to do now is if I take that transfer function that I've created up here, so I'm just going to recall it. Oh, that was the wrong line. I wanted 4, not 5. I can now right-click on this, and you'll see that I have a dynamic systems package that's loaded up, and I can do a bunch of different things with this. So I can potentially take this, I can convert it from a transfer function, I can go to a, let's say, a state space representation for it. So I can quickly and easily manipulate the form that it's being displayed in. I can also right-click, and I can generate plots of this. So I could do, for example, a root locus plot, I could do Bode plots for phase and magnitude, so I can get a lot of vital information from this transfer function and be able to get the appropriate engineering plots to be able to get a visual of what the system is actually doing. Now, what would be nice, as I was referring to earlier, is if there's a way that we could just manipulate some of these things and be able to generate a transfer function, or use this transfer function to create these plots and see what effect changing these particular parameter values down below would provide. So to do that, I'm actually going to load up a new worksheet here. And I'm going to, for the sake of time, I'm just going to copy and paste in a snippet of code here. And what I'm going to do now is I'm going to open up a startup code region, and you don't have to do everything this way. I'll explain when I go through the example what I've actually done in different ways of doing it. But essentially, what I've got here is a piece of code so that I can use this code and some of these embedded components to make an interactive worksheet. So what this is now going to allow me to do is I could take my worksheet and I'm going to put in some dials and gauges and then be able to move those around and then see what effect they have on the overall visual or the plot. So what I'm doing here is, this is with a different transfer function, but you know what? I'm actually going to, I'll use this the same equation that we had there. So just let me copy and paste that in. So I'll do some quick manipulations here on the fly for this. All right, so if I put that in, so I want to use M, C, and D. And instead of using, so I'll multiply that by M, I'll change the 4 to a C, and I'll change the 8 to a D. All right, so what this is now doing is I've created these parameters, and then down here, as you can see, they're basically going to be using these parameter names for the dials once I drop them in, and it will generate new plots for me. So I'm going to save this. And what I'm going to do now is I'm going to drop in 2 plot windows. And then down below here, I'm going to put in a couple of dials. So the dials themselves, if I right click on any of these, you'll see, oops, that was the wrong window that I wanted. So you'll see here that the component property, it's giving me a name, and it's giving me some properties that I can change around in here. So I'm going to just change this. Instead of going from 0 to 100, I'm going to have it go to 0 to 10. So I just need to edit some of these values, so just basically scaling everything down a bit. So that was dial 0, this will be dial 1. And then this will be dial 2. Oh. All right, so now that I have my code and everything entered in, I'm just going to restart my worksheet. And okay, let me see. I must have forgot something here in my 0, 1, and 2, plot 0. All right, I think I just have one piece of my code here that I just have to take a quick look at. Oh, I know what it is that I forgot to do. I have to actually make reference in the component to reference that code. All right, so let me just, so basically what I'm doing here now is I forgot to tie the dial into that startup code that I created. So basically this is a snippet of code here that's just saying to call on that code that I had initially entered in. All right, so let me try this one more time. So restart my worksheet. And now I should be getting a Bode plot and my root locus plot over here on the side. So I can now see what happens as I change particular parameter values around. Now this is just with some very quick and easy examples. Obviously you'd want a little bit more information on here if you to edit this up correctly, to actually let you know what the equation is and what these dials actually relate to. But you could just as easily enter in a math box over on the side, and then it'll show you what the equation is as you move the dials around. Or you could put some extra notes around here to be able to say, okay, this dial relates to parameter A, B, and C, or this one to that particular parameter. But the point of it here is that you can now start to explore and investigate the effects of these parameter values on the overall system.